Today, then, let's take a look at how reactions of aromatic compounds, what types of reactivity we would expect them to have. And hold on just a second while I close this window behind me. And so when we look at different types of reactions of aromatic systems is where we're really going to spend our time for this portion of the unit. And we're looking at things that are in fact aromatic and then trying to predict how would they behave. And so if we have an aromatic compound, we want to be able to say something about their reactivity or the reactions of. Now, for the more eagle-eyed students in here, you might be saying, well, how do we make these aromatic systems? That isn't really too big of a concern of ours right now as a group. These molecules are actually exist in nature, and certainly you can make them by running elimination reactions and such, but we're just going to assume that we have an aromatic molecule. You won't have to assume or know how to make them. They exist in nature, and if they exist in nature, we're just going to talk mainly here about how do they in fact react. And so aromatic compounds, and so we're just going to use this benzene ring as our representative aromatic compound. What I want to say is there are positions right here which is called the benzylic position, and at this position right here there are a slew of reactions that'll take place, reactions that you've seen truly before. This is your substitution type reactions will take place here, elimination reactions will take place there. I'm not going to spend a whole lot of time going over these reactions because really what you saw for just a really simple aliphatic type position, here you're going to see the same exact thing happening on the carbon atom attached to the benzene ring. And so we'll briefly talk about the types of reactions you can expect. You'll notice those, if you're looking on the screen in the bottom left corner here, these are those substitution and elimination reactions. And you won't be seeing anything really too wild here. There's also something called free radical bromination. And there's also this really awesome reaction called oxidation. And these reactions are covered primarily in, what chapter was that? Chapter 17. And then the other types of reactions that we will encounter are reactions that occur in the ring. All right, and those are chapter 18 type reactions that I just switched over to on that tab. And these are things that instill functionality into a benzene ring. And not the best look with that mouse right there. When we look at reactions that add functionality into this ring, it can do a lot of cool stuff. And here's a molecule of toluene, and if you nitrate that reaction, which is reaction number 3 over here, then if you nitrate that thing 3 times, you get trinitrotoluene, which is TNT, and a very explosive result of this adding functionality. So a lot of exciting stuff that I'll get into when we look at these reactions as well. But inside the ring, we're looking at these electrophilic, aromatic substitution reactions. And when we look at these types of reactions, so here's all the reactions you'll have to learn for this portion of the unit are going to fall under really these two categories, which are reactions that occur at the benzylic position, which is chapter 17, reactions that occur on the benzene ring, or the aromatic ring is a better way that I should say this. These things are, these are reactions 1 through 6 in chapter 19. I'm sorry, 18. And then there's a few other types of reactions, and I'll keep this color coding the same, which are reactions then that these undergo. Reactions of the substituents on an aromatic ring. And for us, these are reactions 7 through 10 of chapter 18. And so when there are, in fact, commonality like this where we can group things together, perhaps there is like mechanistic similarity that we could rely on so that memorization isn't as much of an issue. But this starts to break down these types of reactions that we would expect to see in this unit. And it becomes my job in this first part of the lecture today is to talk about these different types of reactions. So electrophilic aromatic substitution reactions, these are like your bromination, chlorination, the fun one, nitration. And when I was in graduate school, I studied these reactions quite extensively, and that one blew up on me in the lab, and that wasn't that much fun when that happened. It was such an explosive reaction. I was holding the round bottom flask right in front of my face with my goggles on, and it was a 100 ml round bottom flask. And when the reaction went south per se, there was this whistle sound, and you never want to hear that in the lab because that means that a large amount of air has just passed over some sort of entrance or exit to something, and that's usually not an optimal situation. And then I heard this quick boom, kind of like a loud flashbang, and none of the glass hit my face because the explosion was so explosive that it when it exploded, it pulverized the glass into sand, and I was just impacted with a fine dust when it happened. So very powerful reactions. Sulfonation is another type of reaction that we will encounter in this unit as well. Friedel-Crafts alkylation and Friedel-Crafts acylation are also reactions that we would expect to fall under the same category. And this is the fun category because all of these share mechanistic similarity. And so we'll dive into that. And so if you can understand what happens with bromination, you'll understand what happens with nitration. That's what I'm getting at there. And then the reactions over here that fall under this category, reduction reactions, turning a nitro group into an amine group, free radical bromination. Hey. From the Department of Redundancy Department, certainly some overlap in that area. Oxidation, it appears like oxidation gets covered twice when we look at this unit. So same exact mechanism there. And then there's this Clemenson reduction as well. And so if I can do my job for you, which I can't help you memorize anything, which is unfortunate. I can't do it for you, but perhaps if I could, as you go through this material, if I can do my job as your mentor, perhaps then I can help you filter and focus some of these reactions down into subcategories. And if those subcategories share similarities, well, then we're in great shape, and that's what we're gonna find. Let's take a look first and foremost at this electrophilic aromatic substitution set. I want to, while you're still fresh, what I want to do is be able to say, let's take a look at how these reactions all follow a similar mechanism. And then once we're done with that, we'll talk about the things that we just added can do. All right, and let's just follow that. We're gonna start with benzene, and we're gonna talk about all the reactions that instill something on benzene. And when they instill something on benzene, it has its function then. And now that we have some function, we're gonna talk about what those things that we instilled onto the benzene ring can undergo. And then we'll talk also about some of these other benzylic position reactions first. Dun, 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 dun. Electrophilic, aromatic substitution. And again, when I took this class, I had a professor that would just breeze through things like that and just assume that I had any idea what he was talking about. What does this mean, electrophilic aromatic system, substitution? Well, it means that we're going to be using our reactant is going to be aromatic. It's going to have that property to it. Electrophilic, electrophilic means we are adding an electrophile to our reactant that is aromatic, and we are substituting something. Something on our aromatic molecule. Spoiler alert, a hydrogen is replaced. Okay, so we could say electrophilic aromatic substitution, and that's the verbiage that I'm forced to use when I talk to smart people like Dr. Ramey. But to me, what I hear is that we've got this aromatic ring, and don't forget that representative aromatic ring that we have here. The implicit hydrogens that I am now making explicit, these ones right here, because we have these hydrogens here, the whole thing is already completely saturated with hydrogens with the exception of this aromatic portion. And so at that moment in time, if we want to add an E to one of these carbons, we're going to have to take away an H. And then that's all it's really what I'm processing when I hear this in my mind. So electrophilic aromatic substitution reactions. General mechanism. And what I'm suggesting here is that all of the reactions, the bromination reaction in the bottom left corner, number 1, the chlorination reaction, number 2, the nitration reaction, number 3, the sulfonation reaction, number 4, the methyl group that was added, number 5, or the acyl group. That acyl is C double bond O with some other stuff attached to it. That acyl group, that carbonyl, that was added as well. All of these reactions, 1, 2, 3, 4, 5, and 6, all followed the exact same reaction mechanism. And so I will represent the Br, I will represent the Cl, the NO2, the sulfonyl, the SO3H, the methyl or that acyl group as just simply with a electrophile, E. And I'm just going to write E plus. And so E could be, it could be this bromine, it could be this chlorine, it could be this nitro group, it could be this sulfonyl group, it could be this methyl group, it could be the acyl group, owning that they're all connected to this. Any one of these things are going to behave in the exact same manner. Well, that's really cool. Our reactant is an aromatic system, and so I'll just be using benzene here. Actually, let me just use a different molecule to spice things up a little bit and drive the people that are just getting good at, oh, I noticed one of you has that really cool the hexagon paper. You submitted your exam on that. That paper is pretty cool, but let's just ruin your day by going with a 5-membered ring right here that is in fact aromatic. This is a molecule called perol. Very important molecule in medicinal chemistry. It is in fact aromatic because it is cyclic. It has a p orbital on every single atom involved in the ring, continuous ring set of p orbitals, here, and here. And then it's got 4n plus 2, where n equals 1 pi electrons. So that's 6 total pi electrons right here. So we're actually in great shape and it's planar. And so we have an aromatic molecule. And what I'm suggesting is that we could add this electrophile to that aromatic system, and what we will end up with is we will end up with an arbitrarily to you, but not necessarily arbitrary, we will be instilling that electrophile onto the ring. Okay. And let me just make this even a little bit sexier and a little bit more explicit for us by saying, if I'm starting with this set right here, scaffold, and I'm just going to draw this double bond in orange right here, and then I'm going to draw in this bond, great, teal, doesn't show up well. Let me pick a different color because I really want to show you where I'm going with this whole entire story. Teal, you're worthless. Pink, magenta per se. I want to talk about where these bonds form too when we look at this reaction with this electrophile. In the end product then, we would expect to see the bonds formed would be using this double bond to form the new bond to our electrophile. And then, believe it or not, when we lose this proton in the last step of the reaction mechanism, the double bond is actually going to come from that carbon-hydrogen bond in the end. And so that's where these bonds are coming from. That's where these bonds are coming from. And so just something to think about. And if I'm doing my job, then that what you just saw right there should be where I get to. So I guess I should say spoilers for that as well. Let's take a look at mechanistically how we would expect this reaction to proceed. And so I'm going to highlight this double bond in orange so we can track that one. And what I'm going to suggest to us is that double bond, and most people on the examination got this right, and I was pleased to see this. A double bond, or a pi portion of a bond is electron rich, And so if there's something that's electron rich, what does the electron rich thing like? The electron rich things like the electron deficient things. And so what's the electron deficient species here? And so we have an electrophile we will add. That makes this double bond behave as a nucleophile. It wants to bond to something with a nucleus, or something that has positive energy, a lack of electron density, or some positivity to it per se. And we have an electrophile, E plus, that will behave as that species. And so we would expect to see the nucleophile attack the electrophile, and there might be something that happens after that. There might be more arrow pushing. There's most likely some sort of, followed by some type of bond breakage. So perhaps this electrophile is attached to some other portion of the molecule, and so what we would see in response to that new electrophile adding is a breakage of some other bond. But regardless of that, we have now effectively instilled our electrophile onto the molecule, and now we have this other magenta proton left, and we have a deficient carbocation over here. There's a proton hidden underneath that positively charged carbon atom that's implicit here, but we have used the electrons to form this new carbon electrophile bond, leaving carbon over here electron deficient, and so we have a positive charge that's occurring right there. And more importantly, we understand aromaticity to be this phenomena, this electronic phenomena that has a really great stabilizing effect to a molecule. And so we've gone from something that's insanely stable to something that is not stable. Most likely, that molecule will do anything that it possibly can to return to that incredibly stable state. And we had talked briefly about this at the end of lecture yesterday, with the fact that if a molecule, when it loses a proton, could become aromatic, then perhaps that really makes that proton acidic. If that charge that's associated with losing a proton can be stabilized in some sort of manner, it's going to make the molecule want to give up that proton, because it has a way of dealing with the consequential thing that happens when the proton is removed. And so when we look at this molecule right here, it's just screaming, holy crap, I have got to get back to aromaticity, and the best way to do that is to give up an atom and steal the electrons to return to aromaticity. This molecule wants to take these electrons and return them to this bond right here, and now we get an aromatic system. It wants to do that. So let me draw the product of that step. We have this electrophile that's attached, and now we would have this thing over here, and arbitrarily we've got a hydrogen now all by itself. And we need some vehicle to make this happen. If the molecule is screaming, I am done. I am moving out. I am taking these electrons that are magenta with me, and you're gone, hydrogen, so that I can be returning to my stable state. Well, then there's got to be something in solution that that can aid in that process, and that aid comes from this molecule that has now adopted the negative charge because it broke the bond with the electrophile. That thing is now very well suited to remove this proton and allow these electrons in this bond, yoink, to return the molecule to aromaticity. And now we have a H molecule instead. And so we have a nucleophilic attack step. and then a loss of leaving group step to generate a aromatic molecule, and then we have substituted the electrophile. Could have been a bromine, it could have been a chlorine, it could have been a nitro group, it could have been a sulfonyl group, it could have been this methyl thing, it could have been this acyl thing that occurs. And so every single one of these is going to follow the same exact type of reaction mechanism. And so we now enter the portion of today's lecture where I will not teach you anything new. And if you start to see the themes, the variations on a theme, if you're a musician and understand classically what that means, that we really have an idea that we're just going to tweak a little bit, like the shaker theme, for instance, that's very, very common. Just variants that can have, but it's obvious that the author of the music is calling back to those themes all over again. I guess you could call this sampling in today's hip-hop music. When that happens, we're going to see that, hey, the core of this sucker is the same, all these reactions. And there might be a slight little variant on the theme, but generally the reaction is going to take place going through the same exact reaction mechanism. And if you're really following me this morning, then in your mind you could be thinking, hey, if there's slight variance on the theme, it's not going to occur in what he just drew right here. If there's any variance, the variants are going to happen almost ancillary to the reaction that's taking place. The variant between bromine and nitro probably has something to do with what's happening right here. Sure as heck not happening right here, because the reaction is the same substitution regardless. We are putting something onto an aromatic ring, and if we're putting something onto that aromatic ring, it's probably going to proceed through the same exact type of reaction mechanism. Let's see this play out now. If my reactant, and we'll go to a benzene ring for this example, if this thing were to encounter Br2 or Cl2, we would expect that the product of this reaction would place one of these chlorine or bromine atoms onto that benzene ring, okay? And we would also have HX as a product of that. And so substituting a proton for a halogen, and what we use here is this thing called AlCl3 as a catalyst for this reaction. And what happens here, pretty straightforward. If I'm going to tell you that we are looking at variants on a theme, then our variants on a theme are likely happening with what's occurring right here, because we already know what the nucleophile is. The variant must be in how we generate the electrophile from X2 and AlCl3, or AlBr3, depending upon what our halogen is. And once we've established how these two things combine to make this electrophile molecule thing, we can just send it through the reaction mechanism. AlCl3 catalyst, and it polarizes the X2 bond. We've made the case that the bond between these two halogen atoms is not static. It is absolutely dynamic. Electrons existing in a dynamic back and forth oscillation between those two atoms when they contribute to the bond. Now, when that's happening, you get a part, when my head is over here, we're thinking that's a negative charge, and when it's over here, it's the negative over on this atom. And so when we look at those things going back and forth, when the electron density is on this side, then over on this side right here, we would expect that to be partially positive. And we would be right. We've seen this before in an alkene reaction with Cl2, for example. So that whole thing, we know that could work here. It turns out that the nucleophile, because those electrons are stuck in the ring, bouncing around everything all at once, they are not isolated. That makes them less accessible, and so they seem to be less negative. And so what I mean by that is, if you are trying to I'll think of an analogy with my child. If I'm trying to gather up my kid to put him into his car seat, it's so much easier if I can pick up my kid when he's preoccupied with his iPad sitting on the couch and just set him in his seat. However, if I let him run around, then he's zipping around space, and I have to try and catch him before I put him in his car seat. And it just, because he has more freedom to roam, it makes him less accessible for me to get into his car seat. And so at that point in time, what I'm thinking is, when we look at these reactions, because these electrons in our nucleophile are zipping around in space, they're a little less accessible. And so what needs to make that halogen more attractive is we have to make it more electrophilic. And that's pretty easy to do, because if we add this Al Cl3, what this does is it just polarizes this bond so that we end up with this Al partial positive, partial negative, partial positive. It just makes this, by polarizing a bond, what I mean by that is that the bond becomes more dynamically skewed between the positive and negative portions when we add that AlCl3. This is now more partial positive than before. And that's all that's happened. And if I can make that statement to you, then can you just stick around for a second when we say, hey, here's the benzene ring, and I'm reacting that with essentially XXAlCl3, wherein this is now more partially positive, and this is still my nucleophile. Well, then, if I have a general reaction mechanism that states one of the pi bonds in my aromatic system will react with the electrophile and something will happen, well, then I have to make the case that that's true. Here's a pi portion that's reacting with an electrophile, and there's something happening as a consequence of that addition to that electrophile, and all of a sudden I have now instilled a halogen atom onto this benzene ring. And right now for this lecture, in 20 minutes, it's going to matter where we put stuff. But right now, since nothing is already on the benzene ring, that isn't going to matter at all. We've added that halogen to that ring, and then all we said is that the next step of this reaction is the molecule screaming to want to return to aromaticity, and it's going to give up something in order to do that. It's going to give up this proton so that it can pick up this set of electrons and return the molecule to aromaticity. And so we have X minus can pick up this proton, and these electrons right here then are suitable for returning the molecule to its aromatic state, and we have now removed this and have HX as a product. I should have done those two in orange, but you guys get the idea. And this last step, usually, you're making a strong acid here, so the case would be like, why not just protonate this thing and go backwards again? And that option is there. It's an aromatic system, so it's slightly less likely to do that. And typically this happens in your separatory funnel instead anyways. Hey, not bad for whatever day it is in 2020. I don't even know what week it is anymore. But whatever day it is, not bad work for a day, because we said, hey, all this stuff is going to follow a similar pattern. Woohoo! If that pattern can be followed, then let's prove it. Turns out the only thing I needed to teach you then is that this species right here is more polarized, and that's how we make our electrophile. Let's try this again. Here is an aromatic molecule called N-methylamidazole. And what I'm suggesting here is that if we have H2SO4 and HNO3 in solution, that we will end up synthesizing, and this is the reaction that blew up on me, NO2, you would end up installing a nitro group to that molecule. This is reaction number 3. So this is reactions 1 and 2. This would be reaction number 3. So bromination, chlorination, nitration, something like that. And so again, I'm betting that it's going to proceed through a similar type reaction mechanism, and the only thing that I need to tell you is how this stuff together makes an electrophile, and that is not obvious. But when H2SO4 and HNO3 combine, they make N double bond O double bond O, and that has a plus formal charge on it. And there's some other atoms that are involved here. I don't want you to get too distracted by you make HSO4 and water as a side product, but this right here, this stuff right here is our electrophile. It is positively charged, that nitrogen, and so we would call that our electrophile. And so by virtue of just a minute with me of saying, hey, if all these reactions that are electrophilic aromatic substitution reactions all proceed through the exact same reaction mechanism, that's good. And then if that's the case, then all I have to do is really show you what is the electrophile. And so once we know what the electrophile is, let's prove to the audience at home that we end up with the same mechanism. We've got a plus charge here. We know, again, we're still dealing with pi portions of molecules, so we know that this portion here will behave as a nucleophile, and we get addition of that nitro group to that aromatic molecule. And I wouldn't expect you to know this right away, or that the carbon right there is the most nucleophilic carbon on the molecule. We end up with the species where we've now added our electrophile onto the molecule. We are no longer aromatic here. Molecule wants to donate this proton to return to aromaticity. Do we have anything in solution that could possibly aid in that process? HSO4 minus generated from the formation of our nitronium ion, which was then our electrophile. Removal of that proton. We're left with that nitro group added onto that molecule, and if you're lucky, it doesn't explode. And if you're a little luckier than that, I guess, is then when it does explode, it doesn't explode all over your face and destroy it. Let's look at this idea of let's take a look at number 5 right here. Friedel-Crafts alkylation. We'll return to our benzene ring example.
Hey, Doc, with the nitration example, would we ever see a bond formed between that positively charged nitrogen and that negatively charged oxygen, or is that because of the resonance between those two nitrates that wouldn't happen?
Thank you for chiming in, and others, please don't be afraid to interrupt me. I'm just kind of here by myself. I do this without an audience too, and so it's great to have you guys ask questions. The question that's fundamentally being asked, if I understand it correctly, is at this point in time, at this point in time with this molecule without that orange arrow, the student that asked this question is asking the most basic, obvious question is, I've got a nucleophile here and I've got an electrophile right here. How come this thing doesn't react? And we'll just do sidebar. In an intramolecular fashion, like this, instead of the sulfuric acid removing that proton. And I believe we would end up making that potentially as a molecule. And I guess I don't know if there's any evidence that that does not happen. It certainly is not observed in any product distribution of or analysis of any products that I've done, and I've spent 7 years dealing with these types of reactions. And if that's not the case, if I've never perceived it, and certainly that could be because I'm not the greatest chemist in the world, but even not seeing that, what would be my explanation at this point in time? I would say that because these electrons in this nitrated portion right here can actually exist in this resonance form as well. And so this negative has now become the double bond here, and we've moved these electrons to this oxygen instead. That has delocalized that negative charge and made this an incredibly well-distributed negative charge, less of a nucleophile to undergo this reaction. And then closing a ring like this, debatably likely to happen. I don't know about that, but certainly I would rest it on that negative charge isn't always their argument and then back out of that answer. But it is a fundamentally important question to ask is, when I have a molecule with the negative and positive charge on it, when I have a Zwitter ionic molecule, why the hell don't those things just react with one another? And I don't have a great answer for that, other than I just don't think that negative is always there enough to make that reaction go.
Okay, I was just curious because it looks possible, but then thinking through that with the ring strain of a 3-membered ring, with that being so high.
Well, you'd still have a 5, 1, 2, 3, 4, 4-membered ring. So we'll split the difference. 3 not good, 4 debatably decent, but not great. Yeah, I think that would probably contribute to it as well. Let's go to this Friedel-Crafts alkylation reaction and follow the same guys as saying, hey, we're going to end up in the same reaction mechanism. Can I make a point with this and say that how is this thing an electrophile? Well, in the absence of AlCl3, that's been a decent enough electrophile for regular substitution reactions to occur. You've seen something like an O minus substitute for that chlorine since you've been looking at substitution reactions. So there's nothing great or really powerful there other than saying that we just don't have a great nucleophile. When these pi bonds are zipping around, it's like trying to corral a 5-year-old after you've given him a pixie stick and put him somewhere, and that's just not easy to do. And so by virtue of the fact that this is not as negative as we would like it to be, then the issue becomes that we need to make this positive that was decent enough when we had better nucleophiles. We have weaker nucleophiles now, and so we have to in turn make this positive even better. The idea, again, don't forget, for molecules that are trying to react with one another in a round bottom flask in a sea of solution, they have the same reactivity considerations that you and I would have if we were on the surface of freaking Jupiter trying to find each other in that ocean that's apparently down there. And that becomes, sure, there's moles of us, so like at some point in time when we start, we're the thing is saturated in half with you and half with me, and so it's easy to find each other initially. But as the reaction progresses and we make more and more product, there are still molecules of me that need to find molecules of you. And if that's the case, if I'm a partial positive and you're the partial negative and we're just screaming Marco Polo to find each other, well, in this case, I'm a decent electrophile and I'm screaming, I'm uttering quietly Marco, and you're the electrophile, but you're the nucleophile, but you're delocalized, so you're not as good, so you're kind of whispering Polo. That doesn't help. And so what I have to do is I have to start screaming louder. And in order to do that, I have to make this positive more pronounced, just like we did up here. So fundamentally then, this AlCl3 is going to behave in a manner that we have seen before, Cl3, Al, and then polarizing this carbon chlorine bond to make this carbon more partially positive, so it is more attractive to that electrophile. So this is now more attractive to our decent nucleophile. Okay, so not so bad. And so let me just show you if this reaction was for something like this ClCH3, then absolutely we would expect this reaction to instill that CH3 onto that molecule, and so we now have toluene instead. So no big surprise there. There's just one thing to look out for. This process that we as organic chemists have instilled and said, okay, I've got this great idea. This great idea is we're going to make this more partially positive. So now I'm screaming Marco out there, and then you can hear me and maybe we can find each other and react. All right, and so that's what we're going to do, but there's a consequence to that. Just like any time that you're trying to be incognito and you make yourself really, really loud, if you've ever played the game, oh, what is it? There's a ton of different good stealth games out there. Metal Gear Solid, for instance. If you make too much noise, then you're gonna. There's other things that could potentially happen. And when you make this partial positive, this proton right here it says, "What's up?" It says, hey, this is your moocher friend, right? At every single friend, I have a moocher friend and I love him to death. But his least favorite attribute of mine is that anytime there's something good going on, and we're just going to call it a partial positive over here. This guy says, hey, I want to get in on this party over here. And what I'm suggesting is if there is a more potential stable position next to this, the consequence of undergoing this type of situation to make the reaction go is that a species like this, Cl3AlClCH2, like this, in these conditions, will rearrange to make that species instead. A hydride shift will occur. I will move a hydrogen and its electrons to the neighboring carbon atom instead. And so what we end up instilling, and we have to be careful of this, is the rearranged product instead. And so just be aware that Friedel-Crafts alkylations, by virtue of having to increase the electronegativity, nope, that's not the right word, by having to increase the positive characteristic of this carbon atom to make it more appealing, Marco, to this weak nucleophile, we also introduce the possibility of rearrangements as a result, and so we will instill the rearranged group instead of the desired group, and so not observed would be that molecule. Major bummer when you're an organic chemist. And we're just going to take a quick second to say, in the system that I've invented with undergraduate students in my laboratory here at App State, because we shrink our reaction environment from the size of Jupiter down into a kiddie pool using our patented nanoreactors, we don't need to make this partial positive more positive because we keep our reactants in something really tiny. And as a result, we can use this species with benzene alone without polarizing it, which allows us to make this compound over here. And so we are able to unlock reaction pathways that have never been opened in the last 80 years in organic chemistry. And that's why our investors are so thrilled with what we're doing because it has so much potential. I have been blabbing for about an hour right now. Let's meet back here at 8 after, and we'll continue our conversation about reactions of aromatic systems.